In the last video, we learned that a probability distribution maps every possible outcome to how likely it is. But there's one problem. Sometimes distributions look like this, separate bars. And sometimes they look like this, one smooth curve. Why does one distribution use separate bars, while another uses a continuous curve? The answer comes down to two terms, PMF and PDF. They sound intimidating, but they're really just two different ways of describing probability. One is for outcomes you can count. The other is for values you can measure. Some variables can only take separate, countable values. How many emails did you receive? You could get 0, 1, 2, or 3 emails. But you can't receive 2.73 emails. These values come in separate steps. We call this a discrete random variable. Other variables are measured. A person's height might be 170 centimeters, or 170.5, or 170.53, or 170.5317. Between any two possible measurements, there are even more possible measurements in between. We call this a continuous random variable. For discrete random variables, we use a probability mass function, or PMF. A PMF gives the probability of each exact outcome. If x is the number shown when we roll a fair die, the probability that x equals 4 is 1/6. That probability belongs directly to the outcome 4. You can imagine each possible value holding a little block of probability mass, which is why it's called a probability mass function. A valid PMF follows the same rule as any probability distribution. Every probability must be between 0 and 1, and when we add up every possible outcome, the total must equal 1. Suppose a vending machine randomly gives one of 3 snacks: chips at 0.5, chocolate at 0.3, and a fruit bar at 0.2. Is this a valid PMF? Every probability is between 0 and 1, and they add up to 1, so yes, it's valid. Now, what's the probability of getting either chocolate or a fruit bar? We just add their probabilities. 0.3 plus 0.2 gives 0.5. So there's a 50% chance of getting one of those two. With a PMF, you find probabilities by adding up the masses attached to the outcomes you care about. Now suppose we tried to use a PMF for human height. We'd need a separate bar for 170 centimeters, another for 170.1, another for 170.01, and infinitely many more values in between. For continuous variables, separate probability bars just stop making sense. So instead of assigning probability mass to individual points, we describe how probability is spread across a range, and that's where the probability density function, or PDF, enters the story. But the PDF has one important twist. For a continuous variable, the probability of one exact value is actually 0. The height of the curve is not the probability. To get probability from a PDF, we need something else, area under the curve. Last time, we learned that PMFs work perfectly for things you can count. But what about things you measure, like height, weight, temperature, or time? These values don't jump from one number to another, they change continuously. Instead of probability sitting on individual values, probability is now spread smoothly across infinitely many values. That smooth description is called the probability density function. Here's the strangest fact in all of introductory statistics. Suppose I ask, what's the probability that someone is exactly 170 centimeters tall? Most people would say there must be some probability. Actually, there isn't. P of x equals 170 is 0. How can that be? Because between 169.9999999 and 170, there are infinitely many more possible heights. One exact value has essentially no width, and something with 0 width contains 0 probability. For continuous variables, probability doesn't live at individual points. It lives over intervals. Instead of asking what's the probability of exactly 170, we ask, what's the probability that someone's height is between 170 and 175 centimeters? Now something interesting happens. For a PDF, probability is represented by the area under the curve, not the height, not one point, the area. You can imagine adding together infinitely many tiny rectangles. Their combined area is the probability. And just like every probability distribution, the total probability must still equal 1 for a PDF. That simply means the entire area under the curve equals 1. Suppose we've already calculated the shaded area, and it equals 0.42. What's the probability that a randomly selected person has a height between 170 and 175 centimeters? The answer is already there. The area is the probability. So P of 170 less than x less than 175 equals 0.42, meaning there's a 42% chance a randomly selected person falls inside this interval. Let's compare them side by side. A PMF is used for discrete variables, things you can count like dice, emails, students. A PDF is used for continuous variables, things you measure like height, temperature, weight. For a PMF, individual values have probabilities. For a PDF, individual values have zero probability, only intervals have probability. And finally, for a PMF, we add probabilities. For a PDF, we calculate the area under the curve. So why should an AI engineer care? Because machine learning is full of continuous variables: pixel brightness, sensor readings, model errors, weights, activation values. Many algorithms assume these values follow continuous probability distributions. Understanding PDFs helps you understand normal distributions, Gaussian models, Bayesian learning, and much more. Today's lesson isn't just about statistics. It's one of the building blocks of machine learning. Remember these 4 ideas. PMF is for discrete variables. PDF is for continuous variables. PMF gives probability at exact values. PDF gives probability through area under the curve. If you remember just those 4 things, you'll never confuse PMFs and PDFs again. Let's test what you've learned with 3 quick questions. First, a fair die is rolled. Should you use a PMF or a PDF? The answer is PMF. Second, a person's weight is measured PMF or PDF? The answer is PDF. Third, true or false. For a PDF, the probability of exactly one value is 0. The answer is true. Here's the one thing I want you to remember. A PMF puts probability directly on individual values. A PDF spreads probability between values across a whole range. Now that we understand how distributions are represented, it's time to explore the distributions themselves. We'll begin with one of the simplest, the uniform distribution, where every outcome is equally likely. And from there, we'll build our way to the famous normal distribution that powers much of statistics and machine learning.